Harmonizing Classical and Quantum Mechanics. So essentially, we will be discussing a semi-classical approach towards quantum mechanics, which is not an approximation but an exact formalism. So if you are bored of doing quantum mechanics with Schrodinger equation, then this might be useful. So to start with, these are the topics that I will briefly talk about. Density operators, which is something that you often encounter when you are doing quantum statistical mechanics. I will talk about a transform, Weyl transform, which could be new to most of you over here. Something that directly follows from the definition, Wigner function. So I will talk about how to extract any idea about the classical limit of a quantum system using the formalism that you already defined, and yeah, that's the whole overview of the talk. So to begin with, most of the people who have gathered over here are first years or second years, right? Like, what are first years? Yeah, so we have a good number of first years over here. So I will start by introducing the basic notions that we have in classical mechanics and quantum mechanics, just to suffice for the ideas that I am trying to present right now. I won't go into the details. I will just define the mathematical background required for the same and some concepts. So why this talk is because people who have done classical and quantum mechanics, they know that we do classical and quantum mechanics in entirely different ways. So you can't draw really parallels between the way you study a classical system and the way you study a quantum system. So can we do quantum mechanics the normal way we do classical mechanics? Normal way. So, or can you do something about it? So that's the whole point of the talk. So in classical mechanics, in order to describe the state of the system, suppose you have a single particle. If you know the position and momentum of the system, then you can describe any mechanical variable related to the system. Say if you know momentum, if you want to know the velocity, you can just divide it with mass and get its velocity. Suppose you want to get its kinetic energy, you can take p square by 2m. So you can extract the mechanical information about the system from its position as well as momentum. Now when you have n particles, each particle can have a x coordinate, a y coordinate and a z coordinate, or in whatever coordinate system that you are working. So that's why there is a 3. So q and q2 are just the position. So that's the standard notation that most of the textbooks follow. That's why I use q instead of x. So q1, q2, etc. to q3n are position, and p1, p2, p3n are the corresponding momentas. Now, once you have state of the system, how do you find observables? What are observables in a mechanical system? Say what I explained: kinetic energy, potential energy, total energy, velocity, acceleration. Such observables can be found out as functions of these variables, these positions and momentas. I gave you an example. If you want to find kinetic energy, take p square by 2. So you use functions of these variables to find physical quantities. So this is the formal definition of Hamiltonian. This is meant for second years who are there. This is the Lagrangian of the system. So you would have seen Lagrangian by now, right? So you sum over the velocities and the conjugate momenta and subtract the Lagrangian from it. This is how Hamiltonian is defined. For people who haven't seen what Lagrangian is, you just take this definition for the time being. So for conservative systems, that is, there is no dissipation is happening in the system, if all the forces acting on the system are conservative, then I simply define Hamiltonian as the sum of kinetic energy and potential. Simple definition. Okay. So now the next question is, how do these systems evolve in time? So now you have positions of particles, you have velocities of those particles, you have momenta of those particles. The next question is, how do they evolve in time? That's the whole point of studying dynamics. The heading, if you look at it, is Hamiltonian dynamics. You want to study dynamics of the system. You want to know how it evolves in time. So for that, we have these two equations. You can derive these equations. You would do that in your classical mechanics course. So qk dot means dqk by dt. It's just the time derivative of position, k position. This is just dou x by dou pk, and this thing which I have written over there, this is called the Poisson bracket. So Poisson f and g are two functions, two arbitrary functions of phase-space variables q1, q2 and p1, p2, etc. Then the Poisson bracket of f and g is defined as sum over I dou f by dou qi dou g by dou pi minus dou f by dou pi dou g by dou qi. This is the definition of Poisson bracket. For the time being, just know that you can write this dou f by dou pi as this Poisson bracket using this definition. This definition allows you to do so. Okay. For this term, you just need that much knowledge about what this Poisson brackets are. That would help. Similarly, pk dot is minus dou h by dou qk, which is pk. Okay. If you have questions, you can stop me. Okay. So, this description of classical systems, it immediately gives a phase-space formulation for classical mechanical systems. So, phase-space formulations are, suppose you have a one particle, say in 1D, okay, a one particle moving in one dimension. So now you have one variable for position and one variable for momentum. An example most of you would be familiar with is the simple harmonic oscillator, one particle simple harmonic oscillator in one dimension. So you have just one position and one momentum. So what I can do is I can make a plot. This is the position and this is momentum. I can make such a plot. This is called the phase space. And how will the state of the system look like in the phase space? It could just be a point, right? Oh, is it visible to all of you? I will write a little bigger. So a point in the phase space would correspond to a particular position and a particular velocity. A point, it corresponds to an x and y. Here x and y are q and p. So it represents the state of the system, right? And how does time valuation occur? So initially maybe the system would be in this state. At next moment it might go here, 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 here. So you can join all these points continuously to get the trajectory of the system. So this is called trajectory. So how does in the phase-space formalism classical mechanics look like? You have a position, momentum, phase space. Points in the phase space are called, points in the phase space represent state of the system. Points in the phase space represent state of the system, and time evolution is described by a trajectory in the phase space. That is exactly which is written over here. So I can just show you a video to just get this abstract idea, to get a more understanding of it. So how does total energy of a simple harmonic oscillator look like? It is E is equal to half k x square plus p square by q, right? Right? Everyone knows this. And for a oscillator system, this total energy is a constant, right? So E is a constant, k by 2 is a constant, right? 1 by 2m is a constant. So if I graph this in this plane, what would I get? Class 11 conic sections. What would I get? So I can write, say, 2 by k, if I write it as alpha square, and 1 by 2m as 1 by beta square, then this would look like x by alpha the whole square plus p by beta the whole square is equal to a constant e. What is this? Ellipse. It's an ellipse, right? So if you try to draw the phase space diagram of a simple harmonic oscillator, what do you expect? An ellipse. And this is exactly what we have seen over here. So when it moves in this direction, you find that this is the x-axis. X-axis corresponds to position and y-axis corresponds to momentum. When a particle oscillates in this way, you find that this in the classical phase space you have an ellipse, and so that's not the point, but just to make sense of time evolution, I have added a point. This makes sense to you? Do you agree that you can give a phase space formalism to classical mechanics, and it's quite simple? Good. discuss about quantum mechanics. So most of you, I mean, you would have seen quantum mechanics in your first chemistry course or something. There you would have seen an approach where you see state of the systems as wave functions, as a functions, right? The approach that I would be taking initially would be slightly different. I would describe them as vectors. So what vectors are? So people who know what vector space is, vectors are elements of the vector space. To first year who doesn't know what vectors are, they are just column matrices. Okay? So I will define. So don't get scared by such alphabets. It's just a Greek alphabet. You can work it with the same way you work with A, B, C, and it's just a Greek alphabet. Most of the people use this particular alphabet for describing it. I also use the same. So this a ket vector psi, we will write it using this notation. It is a column matrix of n complex numbers. They are in general complex. So the psi 1, psi 2, etc. up to psi n are complex, and we will call n the dimension of. So these are vectors, right? So I can take all these vectors together in a set, and I will call that set vector space. And n is called the dimension of the vector space. So if you do linear algebra at some point in your life, you will get to know what all these actually means. But for this talk, I can't introduce entire notions in linear algebra. So if you don't know what that dimension means, take this definition for the time. So once I have a ket vector like this, once I have a column vector, I can define a corresponding row vector, and I will define it in a particular form and call it a bra vector. So once you have a ket vector like this, what I will do is I will write it as a row vector, and I will take the complex conjugate of each of them. All of you know what complex conjugate means? I will take complex conjugate of each of the entries. Now I have a row vector and I have a column vector. I can multiply them, right? So I will multiply this. So I will multiply them, and this product, this particular product, I will call it the inner product in this space. So for the people who already know inner product, this is the standard inner product in CN. Fine? This is the standard inner product that we have seen in that we see in CN. So in case you don't know what an inner product is, just take this definition. We will work it. Okay? Clear? These are just matrix multiplications for the time being. Clear? Question? Okay, now I will introduce something which is called the linear operator. So I introduced ket vectors, bra vectors. I never mentioned how they are being used in quantum mechanics. I just defined them. So I will define something else and I will go to quantum mechanics. So linear operators. So what it does is, a linear operator, it acts on a ket vector and gives me back a ket vector. Okay? It need not be the same. It can act on a ket vector and give me a different ket vector or same ket vector. I don't care, but it acts on a ket vector and gives me back a ket vector. And when it acts in a particular way. How? So if you have sum of two ket vectors, so those are column matrices, right? You can obviously add two column matrices. And you sum them and add the operator on it. It is equal to acting the operator on each of those ket vectors and then summing. Clear? You multiply your column vector with any constant you want, any complex number, and then you add your operator on it. This is equal to saying that you first take, so this a cap is nothing but a function, right? It's just a function. So now you take this, you first operate on the ket state, this operator A, and then multiply it with the C. Both of them will turn out to be equal. That's how I define a linear operator. This is what linearity means. So if I only have, so there in the previous slide, by defining ket vector, I only have n components, right? And this n is finite. For the time being, I don't consider it to be infinite. So what I can do is, I can write this linear operator as a matrix. In all cases, I will be able to write this linear operator as a matrix. So now the immediate question would be, how will you be able to write it as a matrix? Because for writing it as a matrix, you want to know what is the matrix element in each position. Right. For that, so this is not really important for the term, but just for the sake of completeness, I added it. So for people know what a basis is, if you have such a basis for your vector space, then the ij matrix element is just phi I a cap phi. This is just an inner product. So you add a cap on the jth basis vector, take inner product with phi I. This will be your a ijth entry of the matrix. And using this, you can find a matrix. So the take-home message is that if you have a linear operator a cap, which is just a function with those properties, to add it on a column vector, this is just some abstract function. You don't know what that does. What I am claiming right now is that you can always find a matrix corresponding to a cap if that n is finite. And then what you have to do is just multiply your column vector with that matrix. You can multiply a matrix with a column vector, right? And that will give you the result. That's what I'm saying in very simple terms. Confusions? Questions? Fine? See, seniors won't ask any questions over here because they know what basis this matrix is. So if first years have some questions, you have to speak up. They very well know what all these means. So then let me define how we can use all these stuff to define a quantum system. So how did we define state in classical systems? We defined it as a tuple of positions and corresponding momenta. In a quantum system, we will describe state of the system with a ket vector. Okay, ket vector, and you have seen what that is. That is the inner product. So if I take this thing, if I take the inner product of psi along with it, you will get 1. So this is a raw vector, this is a column vector, this is an n cross, this is a 1 cross n vector, this is an n cross 1 vector. So you multiply matrix. So you multiply it, you will get a 1 cross 1 matrix, and 1 should be the entry of that matrix. This is called normalization. You would have seen normalization using integrals, right? You would have seen. First years, have you seen normalization using integrals? Yes. So this directly follows when you are working with an infinite dimensional vector space for the same. So for the time being, this is the definition. Observables are linear operators. You know what a linear operator is, right? Everyone know what a linear operator is. We just saw. But there is an additional condition that you need, that they should be hermitian. What does hermitian mean? What you have to do is, you have this matrix, you take the complex conjugate of each entry of this matrix. Okay? You take the transpose. Then the matrix that you are finally obtaining should be equal to the initial matrix that you started with. So conjugate transpose should be equal to the matrix that you started with, and it gives you a nice property which we quite often use. The property is that, suppose you have a ket vector V. You apply an operator A on V. You take inner product with U. Okay? Now, if that condition is satisfied, then this will be equal to capital A U B. Again, I won't prove this. You will do this in some point of your life. If you are taking physics in your second year math method course, you will find something along the same lines. So you will get this property, and this property is quite critical to quantum mechanics. It gives a lot of important results that we have related to measurement in quantum mechanics. Yeah. Huh? Yeah. That's how I defined it. So what you are saying is that I will have something like this over here, right? But look at state in a quantum system in a state psi. To find expectation value, you operate this operate, you get to find the okay. So first of all, I will have to define what expectation value is. So expectation value, you can think about it this way. So suppose you have a lot of quantum systems all in the same state. Okay, you have a lot of quantum systems, say n many quantum systems, everything in the same state, and you want to measure something, say kinetic energy. What I will do is I will take the first system, make the measurement, label it M1. Then take the another system, make the measurement, label it M2. Remember, all the systems are in the same state. I will do n measurements and then average. Okay, I will do this for a very large one. So then what I will get is an average value of the outcome of this A cap measurement. Average value of the outcome of A cap measurement, and that's what I call the expectation value. And now to do this, you don't really have to prepare any quantum systems in identical state and do all these stuff. What you can do is you can apply your operator for which you want to find the expectation value on the state side, the state of your system, and take inner product result. And that would be the expectation value, the expected value, when you are doing a measurement with this operator. Fine? You will do all these things in detail afterwards. So time evolution is given by something that you would have seen, which is called the Schrodinger equation. So that's just I x bar is h by 2 pi, Planck's constant by 2 pi, I is square root of -1, delta G psi is equal to h psi. You will have to just solve this partial differential equation to get the time evolution. It's not easy as it sounds, it's very difficult in most of it. Oh. Now let's go back. Now see, I assume here that n is finite, right? What if n is not finite? You might think that I will always write an infinite number of psi 1, psi 2, etc. going on up to infinity, right? So have you seen the notion of countable infinity? Yeah. You all have seen. So what if I have an uncountably infinite number of psi i's? What will I do? Then I got no more label it as psi 1, psi 2, etc. up to psi n. What will I do? So then we rely on something which is known as wave function. So usually in the quantum mechanics course we define something called position states and momentum states, and then come to wave functions and stuff. I am not doing it that way because it will take a lot of time, and you need to know some stuff like Dirac delta functions and stuff for that. So that's why I am presenting it this way. So when you have an infinite number of such size, you describe your state using a function of position and depth. Okay? And now, so how did you define inner product? Phi psi? Right. Now, when you have a large number of such cases, and if they are continuous, as in there are an uncountably infinite many of them, we replace this with an integrate. So we integrate phi star of RT psi of RT over the entire space. This is just an integral. You guys have seen volume integral? Anyone? So this is just a volume integral. So in the total space, I would just integrate phi star times psi. At the end, I would get a value. I will call it the inner product in case of infinite dimensional system. And this is quite common to all of you over here. This is the definition of normalization. I mean, this is the kind of normalization that you would have seen in your course, right? Yeah.
So if we're taking DQ here, are we keeping this? Are we considering it to be?
We are considering that we have the wave function spread out in the entire space. It's not in a single line, it's not in a plane, but in the three-dimensional space. That's why I'm taking it.
But it has to be selected.
What symmetry?
Like dx and dy dz, one has to be selected.
What is that property? I have never come across it. Yeah, tell me. Feel free. Tell me. What symmetry are you talking about?
Like why are we considering dx dy?
Oh, okay. So d cube x. This is now dx dx. This is dx dy dx. This is the notation. D cube x is the notation for dx dy. Okay, it's not dx dx, it's dx dy. So this is the normalization that you hope to have seen. Now, observable. Now think about it. Now I can't really talk about metrics. When we talked about metrics, I wrote something called a basis and with n many things. But now if I have a lot, an infinite number, maybe countable or uncountable, now I can't really talk about matrices. But I can still talk about the property that I wrote over there. The property related to inner product. Because I have an inner product here as well. Right? So I will define so in this case, observables would be linear operators with this property, and this property, the operators with this property are called self-adjoint operators. Okay. If you feel that this is a lot abstract, then in reality this is even more abstract. So this is the most I guess simplified. So now expectation value. You act A on side, take inner product inside. Act A on side, take inner product inside. Same thing. Time evolution, Schrodinger equation. So let me summarize whatever I did till now. Classical mechanics, state of the system is described by phase space variables. Quantum mechanics, state of the system is described by get states. Observables are functions of variables classically, but self-adjoint operators in quantum mechanics. Time evolution are given by trajectories in classical mechanics, but in quantum mechanics there is Schrodinger equation to give that, and there is Hamilton's equation to give that in classical mechanics. The question that we are trying to answer is that, can I do quantum mechanics this way? Can I define some phase space variables? Can I define a quantum phase space and then talk about observables as functions of those phase space variables? Can I talk about some kind of trajectories in that phase space? Is that even possible? If possible, how? What do you think? Will it be possible? Can't I just describe a quantum system with just mentioning its Q and P? Second years and first years? Can't I just do that? No. Why? Exactly. Because of the uncertainty principle. Now you can't really pinpoint position and momentum simultaneously. There is some uncertainty involved, and that prevents you from doing classical mechanics quantum mechanics this way. So now what can we do? So for that I will define something which is called density operators. Now I will just go a little bit quick through the definition. So psi is this one is a column vector, right? This one is a row vector. So this is something which we call outer product. So this is an n cross 1 vector. This is a 1 cross n vector. If I multiply them, what will I get? N cross n matrix. So that's why this is an operator. So pure state is that you have just one state. Okay, you are just working with one state, and density operator for pure state. Definition of density operator for pure state is just size, right? So even in infinite dimension, you can extend this. You can have such a notation, and then you can talk about matrix elements and stuff like that. So this definition is not restricted to finite or anything. You can always talk about this in infinite dimensions. Okay. So by definition, hermiticity follows. So trace normalization, I won't get into the proof of all these for the time being. At the end, if someone really want to know the proof, feel free to let me know. I can write it down for you. So what does this mean? Do you all know what trace is? Everyone. It is the sum of diagonal entries of that matrix. Or I won't discuss that. If you know about how that looks like in infinite dimension, then you know. That's it. Expectation value. Okay, this is a very important. This is a very important. Okay, so before that, so you talk about abstract get vectors, abstract linear operators, and stuff like that in quantum mechanics. Isn't it a cooked up subject? Come on. Isn't it something cooked up? Like you are continuously talking about something which is very abstract. You multiply matrices, you talk about infinite dimensions. Like, is it even a physical theory? Do you think it's a physical theory? So we are talking about probabilities, probability waves and stuff like that. Are they physical? Like, after doing all these hectic mathematics and something, I should be able to describe something which is physical to that system, right? Will I be able to do that? Do you do that? You actually does. So how do you do that? Even if you have all these abstract formalism, at the end of the day, you can always talk about expectation values. Right? You can always talk about expectation values, and I did define expectation value before. So that's the expected value. So if you have a quantum system, even if you can't pinpoint what would be the output of a measurement with 100% precision, you can always talk about expectation values in quantum mechanics, and that makes it a physical theory. So for density matrix, if instead of wave function, you can talk about its expectation value of an operator A. That's a cap over here. So expectation value of A cap. Density matrix is an operator. Sorry, density operator is a matrix. A cap is a matrix. You multiply those two matrices. You take the trace of it. That would be the expectation value. For the people who are seeing it for the first time, this might seem quite non-trivial. Maybe. Anyone wants to see a proof? Huh? You want to see a proof? First years and second years can skip the proof. Trace of A cap, rho cap. This is just sum over the basis vectors on which I am defining this matrix. Say I will use J A rho J. This is the definition of trace. Sum over J. What is the density matrix? Psi J. So this is psi J. These are just two numbers I just computed. Okay. Now this is the basis that I am working with. We usually work with orthonormal basis, right? Orthonormal basis, and if it's a basis, it's complete. It spans the space. So sum over J, this thing. This would just be identity, right? So yeah, then it's the expectation value. That's it. So this is trace of rho hat A hat. So keep this property in mind. We will use it quite often. So I'm adding this just for the sake of completeness. Suppose you have an ensemble that is a collection of many quantum states. Say 100 quantum states. Suppose I'm having 100 quantum states. Each quantum system in a state psi m. Okay? The first quantum system is in state psi 1, the second one is psi 2, and so on. So I can define density matrix corresponding to that ensemble of quantum systems. And what I do is, there is some weight factor times psi m. This thing you would know by this time. You just sum over all such psi m. And what is this Pm? This Pm, suppose you have say identicals. So for that simplicity you consider, you have say 100 quantum systems in your ensemble. 30 are in state psi 1, 20 are in state psi 2, 50 are in state psi 3. Okay? So I randomly choose one quantum state, one quantum system from this ensemble. Okay? And it's completely random and these don't have any preference over the others. What would be the probability that I will get the state with state psi 1? 30 by 100, right? This PM is that one. Remember, psi m is the quantum state of that particle, of that, or is the quantum state of that system. But PM is the classical probability. Psi m is something of quantum nature, but this PM is the classical probability of getting that particular system from that system. Okay, so this is how we define density vectors for this. So time evolution is given by something which is called the Liouville-von-Neumann equation, and so H. Okay, have you seen what commutator is? First year? Commutator of A hat B hat is A hat B hat minus B hat A hat equal to 0, right?
What the previous line? So here we define the trace line. So the trace, is it also the same for infinite dimensional space?
Yeah. The thing is that suppose you have a countably infinite basis, even if it's infinite dimensional, suppose you have a countably infinite basis, you define this as sum over I. Say you have a matrix, sorry, a linear operator, right? Trace of A hat is defined as sum over I A hat, I of I varying from unvarying. And now if your basis is uncountably infinite,
So what guarantees that sum will always converge? The sum
we usually don't answer such questions in physics. We always assume that they always converge. See, I am going to define a mode of integral in some time, and that's an integral from minus infinity to plus infinity, and we assume that it converges. So trace of A hat is this. So this I A hat I.
But you do it on Hilbert's page, right? The guarantee is that it will Hilbert's. So that
Hilbert space, what I know is that it is complete.
Yeah.
So if you have a Cauchy sequence of vectors in that Hilbert space, then it will converge in that Hilbert space. That's the very limited knowledge that I know. But this one
is something like a finite ring operator. For it to converge, like the finite ring operators.
I couldn't
Like
say.
for a trace to converge,
Yeah.
the operator should be a finite ring operator. Right?
Operator should be a finite.
Finite ring operator.
Finite?
Rank operator.
Right. How do you? Not very sure of that. I mean, won't be, because I have seen operators. I mean, I can't give you a proof, but I have seen operators which doesn't have a finite rank, but it's trace convergence. I can give you a counter example, but I can't really prove anything related to infinite dimensions for that. Sorry, if you want, I can send you some. So this is the commutator of H is the Hamiltonian matrix and rho. So I H bar del rho by del T is H rho. This is the proof. I won't be discussing proof for that. So what you want to do is you want to do quantum mechanics the way you do classical mechanics, right? So you want functions of phase space variables instead of operators. So how I define it? So Weyl transform of an operator A hat. So Weyl transform, so what it does is it takes an operator A hat and gives me back a function of x and p. This x and p are not operators but just phase space variables. Take this definition and we will see what this definition actually does. Right? At the first glance, I know this looks extremely complicated. It looked extremely complicated to me as well. But this has some very nice properties for you. So take this definition for the time being. I will define a phase space function corresponding to an operator A cap in this format. Okay? This is an equivalent definition. There is a proof in one paper which says this proves that they are equivalent. So that's a quite long proof, so I'm not getting into it. So if you take the Weyl transform of the identity operator, what is the identity operator? It maps every vector to itself. You will get the phase space function as 1. If you map the position operator, see that's an operator. X cap is an operator. It maps it to x, which is just a phase space variable. You just plug in everything over in that integral and it will just turn out to be this. So p cap it maps to p, and x cap p cap it maps to xp plus ih bar by 2. This is just a complex valued function. xp to xp plus ih bar by 2. X and p are real, but this in total is a complex valued function. So what it does is it takes an operator and gives me back a complex value. Now the question is, I wrote here what is x cap p cap. What about the Weyl transform of p cap x cap? If it is the same as x cap p cap, then this entire thing is wrong. Because p cap x cap and x cap p cap are not the same. Because commutator x cap p cap is ih bar. So x cap p cap is p cap x cap plus ih bar. So you can't, if you want to define some transform which maps operator to phase space variables, then it shouldn't match xp and px to the same thing. And gladly Weyl transform doesn't do that. It maps px to xp minus ih bar by 2. Okay. See, when x and p are variables, is there any difference between xp and px? No. Because those are just functions, those are just variables, xp and px are the same. They are different only when we talk about them as operators. Now there is a catch. Small x is the Weyl transform of capital X operator and p as well. But when I multiplied x and p, I am getting something else. I am getting an additional factor of ih bar by 2. So what do you learn from this? So the Weyl transform of product of operators is not the product of Weyl transform of operators. Weyl transform by definition is linear, but the product of Weyl transform of product of operators is not equal to, so Weyl transform of AB is not equal to Weyl transform of A just multiplied with Weyl transform of B. This is a very important property. This is what quantum mechanics does to you. Because if this would have hold that, then most of the headaches would have gone and you would have had a very easy formalism to work with quantum mechanics, and quantum mechanics will never allow you to have such a formalism. So this is an artifact of uncertainties of quantum mechanics, and now you will have to define something for that. And before that, this is a very important property. You can prove it. It's just a 4-line proof, but I require this entire board to write it down. It's just 4 lines, but so I won't write it down for the time being. So if you want to find trace of products of operators, what you have to do is you take the Weyl transform of first operator, you take the Weyl transform of second operator, you multiply it. It's just normal multiplication, and integrate it over the whole space or the whole xp phase space and divide it with the factor of 1. That will give you the truth. So this is something that can be proved from the definition. This is something that directly follows. Okay, now the question is, how do you multiply phase space function? You found that this is W of A, AB is not equal to W of A times W of B. So we define something called the star operator. So we define the star operator in such a way that W of AB will be equal to W of A star W of C. And how is that star operator defined? It's not that we go from here to here, but rather we go from here to here. We have this definition and then we prove that this thing forms. So f star g is defined as f of xp exponential of an operator. This is an operator. This is exponential of an operator. So take the definition of exponential of an operator as this thing for the time being. So e raised to an operator a is just identity plus a square by 2 factorial plus a cube by 3 factorial. Take this as a definition for time being. So now you have exponential raised to an operator. And what is this operator? So f del x del p minus del p del x g. So you see such arrows, right? This means that add del x on the left function, p on the right function. Here p on the left function, x on the right function. So this would be equal to del f by del x, del g by del p, minus del p by del g, del g by del p, del f by del p, del g by del x. This is nothing but the Poisson bracket of f. Okay? So this is just a Poisson operator. It's when you don't have this exponentials and is bar by 2. If you have f and g on this operator, you will just get the Poisson bracket of f and g. But now, for certain purpose, I am defining it in this way, and this has really beautiful consequences. This definition has really absolutely beautiful consequences. You will see it in some time. So I define it this way, and then I have the first property. So in general, this star product, this is non-commutative. You already saw an example where it doesn't commute, xp and px. It weren't the same. So it is non-commutative, but it is associative. You can prove that. So you had this idea of commutator, right? AB equal to AB minus BA, where this is operator composition. Now similarly, using star product, you can define this thing. You already saw that it is not commutative. It is not commutative. Now you can think of this thing, because f star g would not be always equal to g star. So this would give you some value, and you can study that value. And the study of this value is found to be very critical in this Wigner-Weyl formula. So f star g minus g star, f and g are just functions. It is not the properties of f and g, but the properties of star product, which enables us to define something like that, which makes the definition better. So I will move to Wigner function. So Wigner function, okay. Now I define how to study wave. Okay, how to study observables in quantum mechanics. So I didn't actually tell you how to study observables in quantum mechanics as phase space functions. I defined some phase space functions corresponding to observables, right? Corresponding to operators, I defined some phase space functions. Now I want to describe state of the system as well. Only after describing state of the system, then only I can talk about expectation values, which makes the theory physical. So I will define Wigner function, which is the analog of wave function, as the Weyl transform of density functions. We already saw what density operator is. So this is rho, this is psi side, right? Rho as psi side. So this is just a position state representation, position basis representation. Psi of x plus y equal to psi star of x minus y. You integrate it throughout the space, and you will get a function which I call the Wigner function. Now the question is, how does it become an analog of wave function? How can you extract the properties of the system from this? Before that, let's just see some examples. So before going into that, so what we do is, as someone here pointed out, you can't really study quantum mechanics with just with attributing state of the system to points in the phase space, because Heisenberg prevents you from doing it. You can't measure x and t simultaneously. What you can do is, you can talk about probability of a particle being at a particular x and t, right? So this is something analogous to that. This is not exactly that, but this is something analogous to that. Because you see here, this is the Wigner function corresponding to ground state of quantum harmonic oscillator. If you don't know what quantum harmonic oscillator is, take the name from the title. So, for the people who know quantum harmonic oscillator, this is the corresponding wave function, Wigner function, and this is the corresponding Wigner function. And see, I have plotted this in R cube, that is in the real space, right? Is that because I chose quantum harmonic oscillator that the Wigner function is real, or is it always real? But note one thing, this Wigner function is negative over here. This Wigner function is negative over here. So it's positive in some region, but it can be negative. So the first property of Wigner function, the most important one, is that Wigner function by definition will always be real value. It might be quite non-trivial. So just think of it. I can give you an intuition how that becomes real value. We take the complex quantity of this expression. So this e raised to minus I will become plus I. This psi will become psi star. This psi star will become just psi. Right? Now you make a variable change in this integral. Y prime equal to negative 1. So this would retain its form. This would change to psi star of negative and psi of positive, retaining the original form. If you are not able to see that, it's fine, but that's how it works. If you are able to see that, then it's good. Like, it's just two steps. You just take the complex conjugate of this expression, you will find that this is equal to the original expression itself. So Wigner function by definition is always real. Now, I will call this a quasi-probability distribution in 2 minutes. Before that, again Wigner function by definition will be normalized. I defined it using a density matrix.
Could you repeat the definition of Wigner function?
Did you understand wave transform? Something partly. Right. So you can define a phase-space function corresponding to an operator, right? Did you understand what density operator is? So that's an operator. So I can define a phase-space function corresponding to that operator, density operator, using Weyl transform. That phase-space function is called Wigner.
Because the phase-space function of the
Density operator given by Weyl. Now this is, if your rho equal to psi, if your quantum state is normalized, which by definition should be normalized, then it directly follows that Wigner function is normalized. And a very important property is that if you integrate the Wigner function throughout the momentum, if you compute this integral w of xp dp, so p will be gone and you will have just x, you can prove that this would be equal to the probability distribution in x direction, the probability density in the x variable, so in position. And similarly, if you carry out such an integral in x, you will find that this is the probability density in p. So this property tells something about the Wigner function. Usually, when you are doing quantum mechanics, you either work in position basis or momentum basis or in some other basis. If you are working with position basis, you never really do. You have some insights. You never really have some insights about momentum, what happens in momentum. So what Wigner function allows you to do is to visualize your quantum system in position and momentum phase simultaneously, but not exactly, because you can't measure position and momentum.
Can these integrals be negative?
No, it can never be. You can prove that. You can prove that. Because it's essentially because if you make an integral over dp, this dp e raised to minus ip by x bar, it's the inverse transform of Dirac delta, inverse Fourier transform of Dirac delta function. So this just becomes a Dirac delta function. So y will become 0. So this will become psi of x, psi star x, mod psi of x square. That's never negative. Okay. So this is the marginal distribution. So expectation value. So this is where, So you might ask me, why did you call a function which can take negative values to be a probability distribution, a quasi-probability distribution? That's why I called it quasi. It comes from here. This is exactly how a classical probability distribution behaves. If you do some probability, some basics of probability theory in some code, you will find that when you want to find the expectation value of some random variable, what you do is you compute such an integral along with the probability distribution function. Now we see that this w of xp, the Wigner function, does exactly the same. If you want to find the expectation value of an operator A, you take the Weyl transform of A, you multiply it with this quasi-probability distribution, you integrate it, you will get the expectation value. This is exactly how classical probability distributions look like. So this motivates us to call W of xp a probability distribution. Okay? And since it's negative, I can't really call it. So the two conditions are that it should be positive semi-definite, and it should be normalized. Even though it's normalized, it's not positive semi-definite. So I will call it a quasi-probability distribution. This is orthogonality. So this integral would be equal to 1 by h in a product of psi a psi b mod square. You can prove this as well. And if psi a and psi b are orthogonal, this thing becomes 0. So you can define something like this as inner product in the space of Wigner functions. So that's how orthogonality of Wigner functions and stuff like that. So now this thing is, I just added it for the sake of completeness. So the Wigner function can't really take any value that you want. Let it be any quantum state, any pure quantum state. This is always an upper bound for your Wigner. Your Wigner function cannot. So this is a quite very non-trivial thing that I have come across. I initially thought I would avoid it, but this is the most non-trivial thing that I had seen in this. So like the definition itself that you have seen there, it naturally gives an upper bound on the absolute value of the Wigner function, 2 by h. The proof is quite simple, but I won't do that. Final thing, time evolution. So this is how you do time evolution of Wigner function. See, you saw something similar before, right? Time evolution of density operator. So density operator, you had each row there, and you had a dot.
So can you say that Wigner function is allowing us to go in further more resolution
In h bar square, h bar. In 3 slides, I'll go.
No, just I know that what allows you to do so?
In h, that expansion in h bar square, h bar cube, what allows me to do? The definition of star product. Did you find an exponential of I h bar by 2 there? Now when you expand it, you will have h bar square, h bar cube and stuff like that. I will write the exact expression. I will conclude in 10-15. So this is 1 by I h bar. This is the star commutator of Hamiltonian. What is this h? This is not the Hamiltonian operator, but the Weyl transform of h. Because you can talk about the star product of only functions, right? So the Weyl transform of h, this is how you evolve Wigner functions in time. I can just show you. This is something. So yeah, this is something that I did during my last internship, as you can. So the distribution that you see over here, this is the Wigner distribution, which has a peak at the center, the yellow spot that you are seeing. And you can see, I have time about that Wigner function using that partial differential equation. You have some computational methods to do so. And when I did that, so you can find that this follows a spiral. And this is not a mere accident, but this gives you great insights into studying quantum classical correspondence. Because if you have done some planar systems of differential equations or something, then you would have seen phase portraits where you can get spirals, right? You would have seen something like that if you have done so. And you see that for this quantum system, if you try to write the dynamical system corresponding to expectation value of x and expectation value of p, it is linear, and it gives a matrix, and that if I diagonalize that matrix and look at its eigenvalues, the nature of eigenvalues tell me that, or if I just study the trace and determinant of that matrix, it tells me that it would be a spiral, and I can do some calculation to find what exactly is that spiral, and then find that what the classically predicted spiral is, the quantum probability distribution exactly follows. The center of the quantum probability distribution moves to it. This was a very interesting result that I got during my last internship, but this is not really the topic of today's discussion, so I'll skip it. But just know that this is the time evolution of Wigner function simulated using this. So final thing that I want to talk about today is the classical limit. So answering Sandeep's question, I will answer Sandeep's question in the meantime. So a very important risk. Just look at this expression. You had f star g as exponential of is bar by 2 times that Poisson operator, right? So if I just expand this in this format, exp of is bar by 2 pattern in this format, I will get f star g as this. So the first one is just the normal product of function. You evaluate the functions at individual points, you take the product, plus is bar by 2 Poisson bracket, plus x bar order of a term of order x bar square and another term of order h bar cube. Keep this in mind. So if I just take this limit, so when you have this fg, this is f star g minus g star f, right? So it would have an fg term and gf term, but since they are functions, they commute. So fg minus gf is 0. So the only term that will remain with you, the first term that will remain with you is this term, ix bar. So there will be a negative gf, but Poisson brackets anti-commute. So negative gf would be fg. So this will just become ix bar fg, and then higher order terms. Okay. Then I will divide with an ix bar. So I will get the first term to be fg plus some terms of order h bar. They will have order some h bar or higher powers of h bar elements. Right? Then I will take the limit h bar tending to 0. Then what I will remind with this just this Poisson bracket of it. So that's the result that I have written over here. I think I gave you an idea of it. Even if you just write it down, you will get it immediately. So a scientist J. Hancock in his
what is x bar tends to 0?
Huh?
What is x bar?
Okay. So when you are studying quantum mechanics, I expected this question, but not. When you are studying quantum mechanics, you from a class 12 level, when you are coming, you have this definition of h bar to be h by 2 pi, which is a constant. But if you do it on an undergraduate level, or if you do it in a research level, you usually take natural units where h bar equal to 1, and you really play around with h bar as a free varying parameter, which is usually thought of as a measure of how classical the system is, because in the limit h bar tending to 0, xp is is bar, right, commutator of x and p. So in the limit h bar tending to 0, x and p commute. So they can have something called simultaneous eigenstates. They can be measured exactly at the same instant. So all the quantum nature goes away from the system, and you get a classical. Yeah, in the classical. So this is what this is. So a scientist J. Hancock in this paper tells that this particular expression encodes the entire quantum classical correspondence information in the Wigner-Weyl formalism, which is an equivalent formalism for quantum mechanics. So his claim is that this one-line expression, it encodes the entire idea of quantum classical correspondence. Yeah. So this immediately gives you that you had an HW star in the time evolution equation. Now in the classical limit, this just becomes the Poisson bracket of HW, and this is simply the Liouvillean equation, Liouvillean evolution. In classical mechanics, you would have seen that this is just the Liouvillean equation. So now your W, the Wigner function in the classical limit, evolves as a classical variable. That's what we get. So this gives us some insights about the classical limit of systems if your Wigner function is well behaved. But is it always? does this really work? The problem is, can you always take h bar tends to 0, say the limit exists. So you take limit h bar tending to 0, and can you always say that this is the classical counterpart of the quantum system that I am working with? Can you always say that? The answer is no. Because you have a Wigner function distribution, right? But that can be negative. Classically, a negative probability distribution doesn't make any sense. You can't associate it with the classical probabilistic system. You can't do anything like that. So it is pointless in that case. So first thing is that your Wigner function can be negative in some region of the things. The second thing is that how much the distribution, the Wigner function distribution spread usually depends on h bar. So the distribution in X is directly related to h bar. Usually the distribution in P is inversely related to h bar. Not in all systems, but in many systems. So if you take the limit h bar tending to 0, it might come very close in X, but it can have an infinite spread in P. Then you can't really talk about distributions in that case. That's another. So let me summarize. So the conventional way of doing quantum mechanics is the way Schrodinger did quantum mechanics. There are many alternate formalisms for quantum mechanics. Heisenberg's formalism is there. There is path integral formalism. And usually, even though such ideas are explored on an undergraduate level, the phase-space formulation remains unexplored. So this is kept as some great secret and usually not explored in an undergraduate level, even though this can have very beautiful results. Last summer I worked in RRI Bangalore with a professor on quantization in dissipative quantum systems, and this is a machinery that will use extensively. So when you go to dissipative quantum systems, wave functions won't help you. You will have to talk about density matrices. But when you talk about density matrices or operators, that's just an abstract operator or matrix. How will you visualize it? How will you see it? If it's a wave function, you can plot it. But a matrix, what would you do it? What would you do about it? How will you get some visual idea about how your quantum state looks like in some space? So Wigner-Weyl gives a brilliant formalism for that. So I mean, if you want to really enjoy all these things, you have to prove all those results. They have very nice proofs, and it's a very beautiful formulation of quantum mechanics. And remember, this is an equivalent formulation. This is not a semi-classical approximation. This is not an approximation like WKB or anything. This is an exact result. This is an exact formalism. If you do quantum, you can take away Schrodinger completely and do your entire quantum mechanics with this. You saw dou W by dou T is equal to HW Weyl bracket thing over there, right? You can make a substitution W equal to some some function that only depends on time and some function that depends on space variables, basically separation of variables. And then you can do separation of variables on that PD and then change it to an eigenvalue problem. Now, once you change it to an eigenvalue problem, you will find that whatever you did with your quantum mechanics, the Schrodinger's equation and stuff like that, you can do the same thing using Wigner-Weyl formalism. So this is something exact, but what is its advantage? You can study classical equivalence as well, and up to any position you want, because you have a freedom here. This expression, this notion of star product, which we thought would be a great headache for us, in fact is a great headache for us, but this definition blesses us with this expression, where we can study the system in whatever limits we want. You can order terms of order h bar cube or of order h bar square. So this is a curse as well as a blessing in some sense. So yeah, and so you can't really talk about mixed states when you are working with Schrodinger's equation and wave functions. You can't really do mixed states. So what usually people who work in quantum statistical mechanics, the moment they encounter mixed states, they move to density matrices. And when you have density matrices and mixed states with you, this Wigner function naturally incorporates everything into the definition, because Wigner function itself is defined as Weyl transform of density matrix, and it gives you all those descriptions that you would require. And I will just conclude my talk with two quotes from two papers that I have majorly referred. The first one is that, I'll just read it up. It It is the way in which physical results are extracted using not only the Wigner function but also the Weyl transform of the density operator and the star product algebra which accounts for the quantum behavior. You might ask, you are just doing classical things, working with just phase-space functions, their products and stuff. How does quantum behavior appear in the system? Here is the answer to you. It's not just those functions, but the Weyl transform of the operators and the star product algebra, which gives you all these nice results. And I will conclude with this quote. So this is from that same J. Hand paper. In some other part of the universe, Wigner-Weyl approach might be the method of doing quantum mechanics, which would have been discovered the first. So thank you. That's all for the talk. If you want to learn classical mechanics, read Goldstein. First years, please don't read this. If you want to learn quantum mechanics, ask Shankar. First years, feel free to read only the first chapter of this particular book. Second years can go and read it. This is a very nice book. If you want to learn inner products, vectors, vector space and stuff like that, but if you don't really want to go to the abstract side of it, if you don't really want to like learn it from a mathematics textbook, this would be ideal to you. You can go read it. He presents some proofs, but he gives a lot of physical intuition. His first chapter is excellent. And if you want to read about Wigner functions and Weyl transforms, the one which I talked about, if you want to do it very rigorously with proofs and everything like that from the very basics, you can refer to the first paper. They have added all the proofs of stuff that I have written in the appendix. But if you don't want proofs, if you want just the physical intuition and how to work with that, you can write a second. Yeah, that's it. Any questions? Questions? Yes.
Can you still do this if you remove space that's very big?
How many?
If you have, let's say, because that's big.
Yeah.
How do you find the right answer?
Same way.
You have
Position stays when you are talking about. Because what you are saying is that now you have a. Are you saying that now you have a 2x2 system and you can't take the inner product with the position space? Is that what you are saying? Position stays. Yeah, that has a price. So what you do is, so in that case, there is an alternate formalism using Langmuir polynomials. If you want, I can write the exact expression, but I can't really do the derivation right now. You can, if you can write a density matrix corresponding to it. Now, I don't really know if you can study spin with it. Everything doesn't need not have a classical counterpart. That's not my case.
So I'll reframe it. If I do a Weyl transformation of the spin operator, do I get classical phase space?
Yeah, you do. See, the thing is that when you have a class,
You have an